In this lesson, we're looking at the vector cross product. So essentially, the vector cross product can be defined as, if we're looking at two vectors A and B, A cross B will be equal to the product of the magnitudes of A and B and sine of the angle in between. Now, the major difference between the cross product and the dot product is that the vector cross product is designed to give a vector answer. So when you find the cross product of two vectors, the vector answer will be perpendicular in direction to the vectors A and B. So that's really important. The vector cross product is used in a number of ways, but most importantly for us is that it gives a direction that is perpendicular to the two vectors that are used. So consider this. We have vector A and vector B in a plane. Now the angle between them we'll call theta. So this angle here is the angle between, as is with the dot product. Obviously, we'll have the magnitude of A and the magnitude of B representing the geometric length. Then if this is a three-dimensional plane, the outcome, the cross product of A and B or B and A will be perpendicular to that plane. So it's going to be 90 degrees from that plane. And so again, if it's positive or negative, this one will be the cross product B cross A, and this one would be A cross B. There is a directionality factor that comes from the dot product. We generally call it the right-hand rule. So it is pretty much this. If you take your right hand and run your fingers from the first vector to the second, so let's say this is B and A again. If we take our fingers, our beautiful fingers, how good does that look? In that direction from B to A, then we're looking at the cross product B cross A. And our thumb will be pointing in that perpendicular direction, looking at B cross A. Now if we do the same thing, but we have to flip our hand around, and now we're looking at that arrow from A to B, so now our fingers are following that direction from A to B, then our thumb will be pointing down. And so that means that this cross product A cross B will be perpendicular still, but in the opposite direction. So that's number one. Vector cross product will allow us to work out that perpendicular vector. Now, functionally how that works. So if we're looking at the how, the easiest way is not to remember the rule, but understand that we can calculate the vector cross product using the determinant of a 3x3 matrix. Okay, so the setup is easy. If we're finding the cross product between vectors A and B again, so let's say A cross B, that's going to be the determinant of the 3x3 matrix that involves, obviously, direction vectors I, J, and K. So that's going to be our first line. The components from A, A1, A2, and A3, and the components from B, B1, B2, B3. Now, as we're all familiar with the determinant of 3x3 matrix, that's relatively straightforward. So we have I multiplied by our bottom. So we do not consider the row and column that includes I. So we'll have I multiplied by the determinant of A2, A3, B2, B3, subtract J, multiplied by the determinant of A1 and A3, B1 and B3. So again, we don't consider the row and column that includes J, and then finally plus K, and that will be A1, A2, B1, B2. Expanding this out gives us the definition of the cross product in component form. So this becomes I, A2, B3, subtract A3, B2, subtract J, A1, B3, subtract A3, B1, and then we add on K multiplied by A1, B2, subtract A2, B1. Okay, so it's as simple as that. That's how we get the vector cross product using the determinant of a 3x3 matrix. One last quick application We can use this for areas and volumes. We'll just stick to area for this lesson. So if we consider the area of a parallelogram, so area of a parallelogram or a triangle formed between two vectors, and we'll say vectors A and B again, then when we look at those two vectors, and this will just be in 2 dimensions, so this is vector A and vector B. Now, if we consider this as a parallelogram, so let's extend this out, and we can see there's an area in this space. Now, we know that the area of a parallelogram is base multiplied by height. If we look at this perpendicular height and we focus on this angle theta in between, then we should be able to see that the opposite and hypotenuse allow us to use the sine ratio. So h is going to be equivalent to the magnitude of the vector A multiplied by sine of theta. And obviously B is going to represent our base, so that's the magnitude of B. So our area will be magnitude of B multiplied by magnitude of A sine theta, and therefore we end up with magnitude of A, magnitude of B sine theta. Now, because we're not worried about the direction here and we just want the value, we're going to say that the area of a parallelogram is equal to the cross product of A and B. And because the triangle is just half of that parallelogram, the area of a triangle is equal to 1/2 magnitude of A cross B. Okay, as simple as that. Let's look at some examples. Okay, so if we look at this example, it's relatively wordy. It's pretty much just saying find the cross product of vectors A and B, and hence find the vector perpendicular to A and B. Now, obviously, the cross product of A and B gives us a vector perpendicular to A and B. So we could do A cross B or B cross A. It doesn't really matter. They'll both give us perpendicular vectors, and they'll just be in opposite directions of each other. So if we look at cross product of A and B, then that will mean that we're looking at the determinant of the 3x3 matrix, including the direction vectors I, J, and K, the component values of A, which are 2, -3, and 1, and the component values of B, which are 5, -1, and 1. So the determinant of this 3x3 matrix is going to be I multiplied by -3, 1, -1, and 1. Subtract the direction vector J multiplied by the determinant of 2, 1, 5, 1 plus the direction vector K multiplied by the determinant of 2, -3, 5, -1. Okay, so what we get is I multiplied by -3, subtract -1, so +1, subtract J multiplied by 2, subtract 5, and K multiplied by -2 plus 15. So we get -2I plus 3J plus 13K is a vector that is perpendicular to A and B. All right. So hopefully you can see how simple that is. If we had to find the magnitude, then it would just be the magnitude of A and B, which will be square root of 2 squared plus 3 squared plus 13 squared. So in this case, that would be square root of 4 plus 9 plus 169, the square root of 182. So that concludes the lesson on finding the vector cross product.